Hello, class. This is Mr. Hart, and in this podcast, we're going to continue our story of plate tectonics and the history. And if you remember from last time, we talked about continental drift and how Alfred Wegener couldn't explain how the continents were moving. Okay, so he proposes that around World War One, 1910s. Okay, no one makes any major developments on that until the end of World War Two. Okay, because in World War Two they invented a technology called sonar. Okay, and what sonar does is it allows a ship to send a sound wave down, and then that sound wave bounces off of an object like a submarine or the seafloor and reflects back. And based on how long it takes that sound wave to go down and back, you can determine how deep that object is. Now, obviously, this was developed as a war mechanism to detect submarines and things like that. Okay, but after World War II, they start using it for a way to map the seafloor because they're not looking for submarines anymore. They realize they can use this technology to look at how deep the seafloor actually is. And so they developed these ships called echo sounders where they just go around and they look at the seafloor around the entire ocean. Okay, and they get this full-fledged map of the seafloor around the ocean. Okay, or in the ocean. And they find something very interesting. Okay, they find this huge line of mountains, okay, which they call the Mid-Atlantic Ridge, going through the seafloor. Okay, so before then they just thought the seafloor was flat, okay, just filled up with sediment. But they find that it's very dynamic, it varies a lot from place to place. Okay, and we watched this video in class. It's actually a Bill Nye clip, but it's from another documentary series called The 100 Greatest Discoveries. And you can watch it here, but it talks about how these sonar ships went around and they were able to map the seafloor and how strange it was to see all these different mountain ranges and features. Okay, and so instead of having a nice flat seafloor, what they found is that the seafloor actually has different sections, okay, or parts. So the first part is what we call the continental shelf, and that's the part of the seafloor that is still pretty shallow. Okay, this is near the shore. Okay, this is where most recreational ships would be and things like that. Okay, not very far off from the shore, and it's not very deep. Okay, if you're scuba diving, you're in this continental shelf. Okay, that's the only safe place to be if you're scuba diving. If you go too much farther out, then you start to go down this major slope into what we call the abyssal plain. Okay, this is the low, deep, flat area of the ocean. Okay, and this is kind of what you think of when you think of the bottom of the ocean floor. Abyss being very visual, right? Just kind of black darkness. Okay, very, very little sunlight gets down in this area. Okay, it's pretty flat. Then you have what we call the Mid-Atlantic Ridge, which is this mountain range they found going through the middle of the seafloor, or any type of ridge, really. And then you got these trenches, which actually sink down underneath these large continental plates. Okay, and if you could continue this, it kind of sink down underneath like this. And so the seafloor isn't quite static, and it's not quite what they were thinking, where it's just nice and flat and simple. It's actually very complex with different areas. Okay, so we want to know these four parts of the seafloor. Okay, and especially this Mid-Atlantic Ridge, because what they found is the reason that we had this mountain range is because the seafloor actually was kind of spewing out magma at that point, okay, and what we call seafloor spreading, because the magma would come up, it create a mountain, part of a mountain or part of this ridge, and then it would kind of spread out. As new material comes up, it pushes the old material out. So if there's some material that forms right here along this part from the magma, when the new material comes in its spot, let me get a different color. When the newer material comes into its spot, it's going to kind of push it out of the way. And so the yellow will actually shift over farther and farther and farther. Okay, so it might move down this far now. And so over time, if that process is repeated, you get spreading. Okay, so the seafloor is spreading very, very slowly. Okay, from this magma coming up and wedging, coming up and wedging out the old material as new material is formed. Okay, and so we have a mechanism to kind of explain continental drift. We're starting to see some type of evidence that the plates could actually be moving because the seafloor itself is moving slightly from the seafloor spreading. Okay, so let's look at some of the history of how we know this and how this was developed. Okay, this idea of seafloor spreading. And the first major development came from two people named Marie Tharp and Bruce Heezen. Okay, they were two grad students, and they worked together, and they were looking at the seafloor map. And what they realized is that it correlated with the earthquake data of the area. And so we watched the video in class that kind of shows this. But if you can imagine, if this line right here is the Mid-Atlantic Ridge, they would look at the earthquake data around that area, and it lined up perfectly along the Mid-Atlantic Ridge. Okay, almost all of the earthquake epicenters were along the Mid-Atlantic Ridge. And so what they realized is that earthquakes were happening a lot around this area, and this is good evidence that there's obviously some movement going on and some type of some magma flow, some movement, some shifting, if earthquakes are happening, something has to be going on. And so they realized that the seafloor isn't static at this point, it's actually spreading. Okay, it's moving, it's generating magma and things like that. Okay, so this is the first major development in seafloor spreading. Okay, another one is a man by the name of Harry Hess starts to analyze kind of the age of the seafloor, and he realizes that it's getting younger closer to the ridge, and it gets older the further you are away from ridges. Okay, so this map's kind of strange because the land is grayed out and the ocean's in color, which is kind of different from a regular map. Usually the land's in color and the ocean's grayed out, or just a solid blue. Okay, but the colored part is the part we want to focus, the seafloor. And the red line represents the youngest part of the ocean, and the green and the blues represent the older parts. And you can see as they come out from this ridge, okay, it's getting older and older and older. Older and older and older the farther away you are from the ridge. Or it's younger the closer you are to it. And that makes sense, right? If it's generating new material, the new material will be closer to the ridge, and the older material will be farther away. Okay? And so looking at the age, we can see that the ridges are generating this new material, and the seafloor is again spreading. Okay? The next one is a very cool way of showing that this is occurring. This is what we call seafloor magnetism. And so this comes from a key idea that the Earth's magnetic field reverses approximately every 200,000 years, which is kind of weird to think about. If you imagine you had a compass, right now it would point towards the North Pole. Well, in about 200,000 years, it's actually going to point to the South Pole because the Earth's magnetic field is going to flip. Okay, this just happens because of certain processes. Every 200,000 years, you get this magnetic field to flip. And so you may be wondering, why does that matter? Well, it's because of these rock layers. So rocks actually have some magnetic tendencies. They will point magnetically towards one layer or another, or to the north or south, based on when they were formed. If they formed in the time when the North Pole was the North Pole, the magnetic North Pole, then it will point towards that direction. If it was formed when the magnetic North Pole was at the South Pole, then it will be flipped. And so as that new material is formed, okay, material that formed during the normal magnetic polarity, what we call it, where the North Pole is the North Pole, will be facing a certain way, or the magnetic field will be facing a certain way. And then rock that is formed during the other magnetic field, where it was South Pole, will be facing the other way. And so we get this banding, or this layering of normal, then reversed, normal, then reversed. And as new material comes up, if it forms during normal time, it will have normal tendencies. If it formed during the reverse time, they'll have the reverse tendencies. And so we get normal, then reversed, then normal and reversed, then normal, then reversed. And so we can use that to show that the rocks are spreading out, because the new material is coming up and it's forming with that magnetic field that it came with. And then you can see that in another 200,000 years, it's going to flip, and so on and so forth. And so this is actually one way we can use to determine how old the seafloor is. Okay, so this is a really cool method of proving seafloor spreading, because we can see these bands occurring in the magnetic field. Okay, and then the last thing you want to note is that that the trenches are actually sinking material into them. So we'll get to this more when we get to plate tectonics, but this is one of the things that Harry Hess, the guy that was looking at the age, also noticed, because if you're creating material in one spot then you gotta be destroying it in another, right? You can't just be making material without destroying it somewhere else, okay? And so what he realized is that material has to be coming out of the ridge like this. It forms, then it spreads over here, and it gets slowly subducted into the ground. And when that happens, it gets heated by the mantle, it convects, right? It moves around, and then it'll come back up and repeat the process. And so it's going through this big cycle where it is being destroyed and then created and destroyed and recycled and created. And it just keeps doing this over and over and over many, many, many years, okay? But this is another evidence of seafloor spreading, is that not only are we creating it in one place, but we're destroying it somewhere else so that we have a consistent system. So we're recycling it, okay? But there we go. So these are kind of the 4 evidences or 4 ideas associated with seafloor spreading, okay? First of all, that earthquake data that was shown by Bruce Heesen and Marie Tharp, okay, they were able to show that the earthquakes lied along the ridges, which is where the major seafloor spreading was occurring. Okay, they were able to show that the age of the seafloor is getting older away from the ridges. We're able to analyze the magnetic layering, which is switching every 200,000 years. And then we can also see that the material is being destroyed in the subduction zones near the trenches. Okay, so there we go. So these are the 4 ideas we want to understand with seafloor spreading. Okay, and so this is the next major development. So we had continental drift. Now we have seafloor spreading. Next time we'll get into plate tectonics. Okay, and so hopefully that makes sense. Let me know if you have any questions, and thank you for watching.